Hello everyone, welcome back to this channel. So in this video, we are going to look into IGCSE Physics Chapter 13, Light. So here is some of the properties of light. First one is that they travel in a straight line, and you can show that they travel in a straight line by using two different equipments. The first one is ray bulbs. So basically, there's a light bulb here, but then because we are putting this card here, it creates a narrow beam of light that showcase that the light actually travels in a straight line. Same goes to the laser light. So let's think about now what happens when we stand in front of a mirror without any light. Okay, so when we stand in front of the mirror without switching on the light, we wouldn't probably see ourselves. And the reason is because reflection of light does not occur. So this is what happens when you stand in front of a mirror. So the light ray, either from your light bulb or the sun, they will hit your body and then get reflected to the mirror. And once again reflected back to your eye so that you can see yourself. Alright? So to understand reflection, there are a few terms that you need to get familiar with. So the first one is the incident ray, which is the light ray that is hitting the surface. And also the reflective ray, a ray of light which has been reflected from a surface. Also the normal. And the definition of normal is that it's drawn at 90 degrees to the mirror. So to show you that, just know that this is the mirror. Let's imagine that. And the normal is drawn in such a way that it is 90 degrees to the normal plane. So I'm gonna color it in red color. So this is a 90 degree, and therefore the normal line is drawn 90 degrees to the mirror. So the fourth term is the angle of incidence, which is the angle between the incident ray and also the normal, and also the angle of reflection, which is usually equal to the angle of incidence. So here is some of the misunderstanding. To measure the angle of incidence and reflection, we use the angle that is what I would say sticking to the normal, not the one that is sticking to the mirror plane. All right, so that's reflection of light. And in reflection, there's a law called the law of reflection. It says that the angle of incidence must be equal to the angle of reflection. So the law of reflection also works for curved mirror. So if in my case, if this is 35 degree, then the angle of reflection will also be 35 degree. And let's explain, why does the image form on the mirror appear to be behind the mirror? So in this case here, why is this object here, even though it's not actually there? So to understand this, you need to understand something called the ray diagram, which is the path which the light ray travels. So in this example, I have a candle facing a mirror. Okay, so what happened is that when the light ray will hit the mirror and then reflect back to the user eye. But then humans are actually evolved to always see light traveling in a straight line. And that's why we see that um, this is actually the image that the user is seeing. In reality, no light is actually coming out from the mirror. What the user see is called a virtual image. So here is the definition I found online, which is pretty useful. A virtual image is a fake image that you can see, but you cannot touch or capture it on a screen, like a projector. It is formed by light ray that seems to come from a certain place, but they don't actually meet there. It's like seeing a reflection in a mirror. The image looks real, but you can't touch it because it's not really there. So here is some of how we can describe the characteristic of the image form by reflection. First of all is that it will be the same size. You won't see a bigger version of yourself in the mirror, right? Second one is that the same distance behind the mirror as the object as in front of it, meaning the distance between distant image and the mirror and also object in the mirror will be the same. Next one is virtual. It's as mentioned, it's not an image that is actually real, it's virtual. Laterally inverted, this is a little bit interesting. Laterally means left and right. So laterally inverted means the left and right are inverted. So you can see that two images here, they are laterally inverted. They're not quite the same. Okay, so here are just some of the definitions for you to understand before we proceed to the next subtopic. Image is what we see when we view an object by means of reflected ray, laterally inverted, left and right reverse. Real image, an image that can be formed on the screen like a projector or your phone. Virtual image, an image that cannot be formed on the screen, which is like the image you see in a mirror. So to show you the ray diagram again, so this is something that you are required to do in your exam, which is to draw the ray diagram. So I'm just gonna draw, let's say we have an object here called O, and to draw the ray diagram, I just draw the angle of the incident ray. Okay, so because it is a reflection phenomenon, just know that the angle of incident must be equal to the angle of reflection. I don't have a protractor here, but then you should draw it in a way that the I and also the R are equal. So let's draw another light gray. Let's do blue color. So that's the same thing. I have the normal line, which is perpendicular to the mirror, and then again the reflected ray. So how we can see the image form is because the image form on the mirror is a virtual image. So you need to extend your reflected light ray backwards. Just extend it until we can find an intersection between two light ray. All right, I'm a bit off here, but then just know that the image will look like this. So that will be the image. So to show you a better version of the ray diagram, I've prepared a completed slide. So this is the better version. This is exactly what I draw. I draw it angle of incident equal to angle of reflection, and then extend the lines backward until I see an intersection, which will be the image I. As you can see that the distance between image and also the mirror, and the distance between object and the mirror should be the same, because that's one of the characteristics of image form in a mirror. So let's look into another subtopic called reflection. Refraction occurs when a ray of light travels from one medium to another. So it explains some of the phenomena we see, like why is straw bent in a liquid, and also why we can see ripples in water. So very similar to reflection of light, we have incident ray, but now instead of seeing the reflected ray, we have the refracted ray. So with the refracted ray, we also have the angle of refraction, which is the angle between a refracted ray and also the normal to the surface at the point when it passes from one medium to another. So notice that light only bends at the point it enters. So if we look at this part, when light travels from air into the glass, this is the point which light ray is refracted, not inside. And similarly, when it travels out of the glass, it will also get refracted again because now it is traveling to a different medium. So when light travels from air into glass, we will see that the ray bends towards the normal, whereas if towards the normal means the refracted ray is a little bit has lower angle than the incident ray. Whereas if the light travels from the glass to the air, the ray bent away from the normal, meaning the angle of refraction is bigger than the angle of incident. So it doesn't only apply to air and glass. Just know that refraction occurs when light travels from one medium to another. Therefore, it could really be anything. So what I'm showing here is just that when light travels from a less dense medium to a denser medium, it bends towards the normal. Whereas if light travels from a denser medium to a less dense medium, the light will bend away from the normal. So that is how it works. And if the light ray hit a boundary at 90 degrees, then nothing is going to get refracted. And why is light even got refracted, right? And the answer is because it travels at different speed and different materials. So to show you, this is something I got from a textbook. So just picture a truck wheel slipping off the road into the sun. So it just kept moving until it suddenly lost control and moved to the sun. The truck will turn to the side because now it cannot move so quickly through the sun. So this is phenomenal to help you understand why does refraction actually occur. So there's another question is that why the swimming pool appears to be shallower than it is. So look at this ray diagram here. Just imagine that there's a stone at the bottom of the swimming pool. But if we were up here, what we're gonna see is that, oh, the rock actually appeared here instead, not so deep. And the reason to explain this is because light is actually refracted when it leaves the water. So water is a denser medium, therefore light ray will travel away from the medium and it bends away from the middle. So because human has been evolved to see everything, including like traveling in a straight line. So what we see here is that the extension of this refracted ray. So that's the rock that we see, but in reality, this is where the rock is located. So that's all about refraction. And in this video, we also talk about the refractive index, which measures how much light is bent because different materials going to bend light differently. So in order to calculate, quantify how much a material can bend something, we have something called a refractive index, which can be calculated using the formula here, sine I over sine R, in which I is the incident angle, and also R is the refractive angle. So let's look into some of the examples to learn how to solve this question. So let's say a ray of light hits the surface of water at an angle of incident of 30. It is refracted at an angle of refracted of 22. Find the refractive index. And that's pretty simple, right? We just use the formula. The N is the symbol for a refractive index. Sine I and over sine I is the formula. All I need to do is just substitute my answer into my value into my equation. And if I were to put everything into the calculator, I'm going to get 1.33. So it is the refractive index of water. So just note that incident index, refractive index, they do not have an index, do not have a unit. All right, because it's ultimately it's just a ratio. So another formula which we can use to calculate refractive index is to use the speed of light in air or vacuum divided by the speed of light in that particular medium. So that's another question. The speed of light in air is 3 times 10 to the power of 8. The refractive index is 1.25. Calculate the speed of light in water. So I'm just going to use the formula. One of it is the speed of light in vacuum. One of it is the speed of light in the medium. So using the formula, I can substitute my refractive index into the formula and also the speed of light in vacuum and then calculate what's my M is. So I'm going to do this. And if you were to plug everything into the calculator, you should get the answer 2.4 multiplied by 10 to the power of 8 meter per second. So that's how we solve refractive index question. And let's move on to the third subtopic of this chapter, which is total internal reflection. It actually involves both theories that we learned previously, which is the reflection and refraction of light. So let's look into it. The definition of total internal reflection is when a ray of light strikes the inner surface of a material and 100% of the light is reflected inside it. So the way I can explain it is that light is refracted when it travels from one medium to another, but sometimes not all the light is getting reflected. So let's look into some of the examples to understand what I'm saying. So In the first phenomenon here, the angle of incidence is quite small. And because the light is traveling from a denser medium to a less dense medium, the light ray bends away from the normal. And if you were to carry out this experiment, you'll actually see that there is a faint reflected ray, meaning some of the light, instead of going out of the medium, the glass, it is reflected within the glass. Okay, so let's see what happened if I were to increase the incident angle. So when angle of incidence increase, you see that refractive angle, because they are bending away from the normal, now they will bend even further from the normal. And the reflected light here will start to get stronger and stronger until a point which we increase the incident angle until its critical angle. So this is when the reflected ray will lie entirely parallel on the plane. And the angle which we need the incident angle to have this phenomenon is called the critical angle, which I'll talk about it more. And when you increase the incident angle more than the critical angle, you're going to see that all the lights will now reflected inside the block. There's no longer light being traveling out of the glass. All the light is being reflected. So if here we have a line, if the angle of incidence is greater than the critical angle, now the light is entirely reflected inside the glass. And it's called total internal reflection for a reason. Total, meaning 100% of the light is reflected. Internal, because this reflection happens inside the glass. Reflection, the ray is entirely reflected. So now I will talk more about critical angle. So basically different medium have different critical angle, meaning it's easier for a certain object to have the light internally reflected than the others. So the critical angle for glass is 42, for water is 49, and for diamond it's smaller. It's only 25, meaning as long as the angle of incidence is greater than 25, total internal reflection will occur. That also explains why is that the diamond, light entering a diamond, are very likely to be total internally reflected, because the light bounces around inside the diamond and emerging from one of the diamond cut faces, because light is still completely reflected all the time, and that's why you can see the blink blink phenomenon in the diamond. So to give you a formal understanding of critical angle, I have definition here. It is the minimum angle of incidence at which total internal reflection occurs, and every medium has different critical angle. So critical angle depends on the materials through which a ray is traveling. The greater the reflective index of the material, the smaller the critical angle, and vice versa. So that's the relationship between refractive index and also critical angle, refractive index. Critical angle formula. So here is some formula you can use to calculate the critical angle of a medium. N stand for the refractive index, C stand for the critical angle. So given the refractive index, you will be able to find the critical angle of an object and vice versa. So let's solve some questions. Find the critical angle C for diamond. Assume that refractive index N equal to 2.4. And that's easy. I can just substitute 2.4 into my equation, 1 over sine C. And because we want to find a critical angle, we need to make C our subject. I'm first going to move this 2.4 around and then continue here. To find C, you just need to move sine to the other side. Just know that you can do sine -1 inverse. And you can calculate the value using a scientific calculator like myself here. Just find the sine inverse symbol. So that's called sine inverse. So let's look at the solution. If you were to key everything I've just written into a calculator, you should get the answer 24. By the way, if you're watching until this far, I hope the video has helped you. But if you are a teacher or student who like to purchase the slide mentioned, you can always look up my website, and that would really mean a lot to me. Thank you so much for supporting. So let's move on to some of the application for total internet reflection. One thing is telecommunication, telephone messages, and other electronic signals. If you study computer science, these electronic signals, be the 0 and 1, they are being passed through fine glass fibers in the form of flashing laser light. And the reason they use light to transmit data is because light can travel super quickly. And inside a fiber, light travels by total internet reflection. So that's how light can travel. It bounces along inside the fiber because each time it strikes the inside of the fiber, its angle of incidence is greater than the critical angle. This means no light is lost as it's reflected. So to show you the diagram, so this is how it looks like. So let's say this is the optical fiber, and I'm going to represent the light in a yellow color. So light travel from here to here, and because it has an incident angle that is greater than critical angle, it's going to get refracted again and again and again. So I'm going to draw another refraction. So again, in this part, they are going to get reflected again all the way until the end of the fiber. And that's how optical fiber work. Hopefully this illustration, helps you. Another application for total internet reflection is the endoscope. It basically is a cube version. Endoscope is used by a doctor to see inside a patient body. A bundle of fiber carry light down, while the other bundle carry the image back up. So that's all about total internet reflection. Let's look into another very, very important for this subtopic for this chapter, which is lenses. Just imagine this. Without lenses, all these equipments here could not exist. And hopefully you can see how impactful the stuff that you are learning now. So there are two types of lenses in which we will learn. The first one is converging lens. As implied by the name, it will converge all the lights that travels through it. So that's when the converge part happens. Whereas the other lens is called the diverging lens. It causes the ray parallel to diverge from the principal. So it basically causes the light ray to spread out. So let's look into the converging lens first. There are a few terms that you do need to take notes. First one is principal focus. Principal focus is the point which all the light ray intersect. So that's the key thing that you need to know. And focal length is another point. Focal length is the length between the center of the lens and also the principal focus. All right, so just remember these two terms for now. And let's look into how a converging lens work. So if you were to emit light into a converging lens, they are going to converge it and then spread it out again. And if you were to put in another converging lens, they are going to return to the normal parallel shape again. So that's how some of the effects on the converging lens. And also, the thicker your lens, the shorter the focal point will be. So in other words, feather lens will have shorter focal length. So that's another thing. Here's a few definition that can help you to describe the image formed on a mirror. Not a mirror, by a lens. First is whether it's in either or thing, whether it is enlarged or diminished. So if you were to use magnifying glass, the image will be enlarged because that's what the word magnified means, whereas diminished means the image becomes smaller. Also, the image could also be either inverted or upright, thus the image appear to be upside down of each other. So that's the definition of inverted and upright. And in order to help you understand the concept even better, we're going to look into how to draw a ray diagram. And then we'll relate the ray diagrams here to all the characteristics of the image. And okay, besides enlarged or diminished and inverted or upright, we also have two more, which is something that we learned already, which is virtual versus real. And virtual is an image that cannot be formed on the screen, whereas real is an image that can be formed on the screen. So that's basically it. So let's try to, I will now teach you how to draw the ray diagram. It is super fun to draw it, so let's do it. Draw a ray diagram to find the image form of a 3 cm tall object. Place 12 cm from a converging lens, it's a converging lens, which has a focal length of 5. Focal length of 5 means this is when they intersect. So now, since we have grid here, I'm just going to assume that one grid is equal to 1 cm, right? So the first thing you need to draw is the principal axis. You just draw a straight line here. And then since they said the word converging lens, I'm going to draw a converging lens. Just forgive me for not being able to draw it very nicely. So let's look into how we can draw the entire ray diagram for this example. So the question said that we have a 3 cm tall object placed 12 cm from the converging lens, meaning we need to draw an object 12 cm from the converging lens in the center. So I'm just going to go through 12 boxes. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is the point which I should place my object, and the object is 3 cm, and therefore I'm just going to do a 3 cm object here. So notice I only take up 3 grids, and I draw an arrow to represent. So that's the object. So now we can start to draw the ray. And there are only 2 rays that you need to draw, 2 light rays. And the first ray, let me show you, is first you need to draw a straight line until the center of the lens. So remember that the light ray will then be bent due to refraction, but I need to know where the light ray will intersect. So this is why it's important to label the focal point. So now I'm just going to go to the center of the lens. I'm just going to count 5, 2, 3, 4, 5, because 5 is my focal point. I'm going to do 5, 3, 4, 5. So that will be my F. And once you have the F figured out, everything becomes easy. You just direct this light ray towards the focal point. And that's it. That's the first light ray that you need to draw. Then second light ray, again, you start from the object, you draw a straight line, but now you convert it to the center of the lens, which is located at the principal axis. You just draw like that. So meaning your light ray has to intersect with the center of the lens. And there you go. We have our image form. Let me represent it using red color. So because the image is formed here, I inverted them. And then so that's my image. So one thing to observe we need to observe is the characteristic of the image. First, we need to answer the question whether it's enlarged or diminished. So if we look at object here, it take up 3 spaces, meaning it's a 3 cm object, but the image only take up 2 spaces, meaning that the image is actually smaller than the object. Therefore, the image, we can say that the characteristic, first one is that it is diminished. It gets smaller. Alright, the second question is whether it's inverted or upright. You can see that now the arrow is now the upside down of the object. Alright, it's upside down. Therefore, it is not upright, it is inverted. Next up, from the ray diagram, you can see that now the image is formed by intersections of light ray. And when this happens, it means that this image is a real image. I understand that it's a little bit hard to figure out what's happening here, but we will have more examples later to show you the differences between an enlarged or diminished object, an upright or inverted object, a real or a virtual image. So that's the answer, and that's the characteristic. The other one is closer to the lens than the object, which is correct. So let's move on to seeing some of the ray diagram for different applications. So we have magnifying glass. Magnifying glass also uses converging lens. So here is the ray diagram for magnifying glass. And the object is always placed, let's say in this example here, 2, 3, 4, 5, the focal point is here. 3, 4, 5. And when we use a magnifying glass, we always place it close to the object, meaning the object will always appear before the focal point. This is why I put it near close by. And when I draw the ray diagram here, you can see that none of these light intersect with each other. In fact, they go even spread out. And therefore, again, just like what we learned in the reflections of light, we always extend it backwards, and then we form an image. So this is when I have an upright image instead of an inverted image, because I have an up arrow instead of a down arrow. It is also an enlarged image because now you can see the image is much bigger than the object. The third one is that it's a virtual image. Virtual image is another thing. The image doesn't form by the intersection of this light ray. Instead, it's formed by the extension of this light ray at the back. Therefore, we call it a virtual image. So that's magnifying glass. Let's look into another application of lens is to correct eyesight problem. If you are wearing glasses, I didn't wear glasses, so if you are wearing glasses, this will relate very much to you, which is why is it that some of the people that need glasses and some they don't? So here's some knowledge. Our eyes actually contain converging lenses that helps us to direct the light onto our retina. So, however, some eyes are unable to change their strength. The kids cannot focus, they cannot converge the light because it either goes too it either got weak or that it's a genetic problem. So here are some of the application of lens that can help solve this problem. So the first problem we have is short sight, meaning they cannot see distant. People with short sight cannot see clear image of distant object. And here's the reasoning. It's because the converging lens of that person is not strong enough to converge all the light to the retina. In fact, they only converge it here. This is why sometimes people only see blurry image because the light isn't really converging. So in order to solve this, we can use a diverging lens, meaning like that. We just spread the image out, and then once it get converged, the light can intersect at the retina of that person. And because we have different power, so the thickness of the lens depends on how severe your problem is. All right, so that's short sight. For short sight, the solution will be a diverging lens. So as in my graph, I will talk about long sight now. They can see distant object but cannot see close object. And one reason is because the eyeball is a bit too short, and the second is that it cannot be strong enough to converge it. Therefore, the light ray actually move past towards the retina. So to correct this, I just need another converging lens to help the eyes to converge the light. So that's what's happening here. So in other words, to solve long sight problem, we need a converging lens. Okay, so that's the last part of our video, dispersion of light. This experiment is quite fun. You can look up some videos online. It says that when white light passes through glass, it refracts as it enters leave the glass and can be split into a spectrum of color. For your information, white light here, they are basically a combination of different color. And when all the colors come together, they become white light. That's why when you emit white light to a prism and that refraction occurs, because different colors refract differently, they refract at a different degree. Therefore, you can see this beautiful mixture of colors. And so that's basically dispersion. This separate different wavelengths of light because they are refracted through different angles. So these are the 7 colors, which is also the colors of rainbows. And dispersion occurs because each color is refracted by a different amount. So as I said, light is a combination of different colors. So when it travels to another medium, because these lights refract differently, you get to see different colors. Red color refracts the least, while the violet color refracts the most. So, but of course, if you were to emit a monochromatic light, which is a light of single color or frequency, not white light, it will be refracted so that it changes direction, but it is not split up into spectrum. Dispersion of light also explains the rainbow's phenomenon when the white light actually travel past the droplets of water. Again, water has a different density, therefore light will be refracted, which is what causes the rainbow phenomenon. And when the light travels into the water droplet, total internal reflection also occur, which is what allows us to see the reason that we can see the rainbow today. So let's try to solve three different positive questions. Which of the diagrams show both the correct position of the image and the correct path? So just this is the candle. We know that light ray should travels like that, and then since it's a mirror, it's gonna get refracted, and the image can be formed by extending the line backwards. So looking at all the answers here, the only answer that is correct is this one. So the image is formed like that. So the answer is D. Great. So the second question, the diagram shows light passing through from air to glass. A number of angle has been labeled. So remember, they said which coefficient should be calculate refractive index. The formula of it is n equal to sine I over sine R. I stands for the incident angle. So the incident angle of this diagram here is the angle which the light ray hit the glass and the angle which sticks to the normal line. Whereas the refractive angle is this one. So in other words, our equation should be sine P over sine S, and which leads us to our answer here, which is A. So the third question, the optical fiber is made of glass that has a refractive index of 1.4. So meaning n equal to 1.4. No light refracts from the fiber. Calculate the minimum angle of angle I for there to be no refraction. So they are basically asking what is the critical angle, because to have no refraction, like all the light reflected, I has to be equal to the critical angle. So that's when we can use the critical angle formula, n equal to 1 over sine C. 1.4 is the refractive index. C is the critical angle we want to find. I'm just going to do sine C equal to 1 over 1.4. C equal to sine minus 1 inverse 1.4. If we were to key everything into the calculator, you should be able to get the answer 46. And that's the end of this chapter. Let's go back to the first slide. In this video, we have talked about the reflection of light and refraction, total internal reflection, lenses, and also dispersion. I hope you learned a lot. Please let me know if you have any confusion. I will gladly help you in the comment section. And I will see you in the next video. Thank you so much for watching.